You search films about a lonely robot, and you get back movies that don't contain a single one of those words. Somehow the computer understood what you meant, not just what you typed. That same trick powers Spotify knowing your next song, your camera roll finding every photo of your dog, and the AI answering questions about your documents. One idea sits under all of it. It's called an embedding. And it's the answer to a deceptively hard question. How do you get a computer, which only understands numbers, to understand meaning? Let's break it down. This is the piece my other videos kept leaning on but never fully explained. Here's the core problem. To a computer, the word cat is just 3 symbols. It carries 0 meaning. Obvious fix, you say, give every word a number. Cat is 1, dog is 2. But that breaks instantly. If cat is 1 and dog is 2, then dog and the word you numbered 3, say airplane, look equally close to a dog. Nonsense. A plain ID number tells you which word it is, but nothing about what it means. So here's the real goal. Represent each word as numbers, where words with similar meanings end up with similar numbers. Where the distance between two things reflects how related they are. Nail that, and meaning becomes math. That's an embedding. Here's the key mental shift. Stop thinking of a word as a label and start thinking of it as a location. Start simple, one dimension. A single line from cold to hot. Freezing sits at one end, boiling at the other, warm in the middle. That line captures one aspect of meaning, temperature, but words have way more than one, so we add another axis, say cheap to expensive. Now every word is a point on a 2D map, capturing two qualities at once. Add a third axis and you've got a 3D cloud. And watch, fruits drift together, animals cluster over here, vehicles over there. Similar meanings share a neighborhood. An embedding is exactly this, a word's coordinates in a space of meaning, its address. And once meaning has an address, a computer can finally do math on it. Now 3 dimensions is what we can picture. Real embeddings use hundreds, sometimes thousands. I'll be honest, nobody can visualize 500 dimensions, including me, so we draw 3 and imagine the rest, but the idea scales perfectly. With hundreds of axes, the model captures hundreds of shades of meaning at once, living or non-living. An action or a thing, formal or casual, positive or negative. And no human labels these axes. The model invents its own during training, whatever best captures meaning. So in practice, a single word's embedding is just a long list of numbers. That list is its coordinates in that huge space. Looks meaningless to us, but to the model it's a rich, precise fingerprint of meaning. And here's the result that made people fall out of their chairs. Once words are points, the directions between them carry meaning too. Take the arrow pointing from man to king. That arrow, it turns out, roughly represents the idea of royalty. So if you take woman and follow that same arrow, you land on queen. You can literally do arithmetic on meaning. King minus man plus woman equals queen. Or Paris minus France plus Japan lands on Tokyo, the capital city direction. Now, real talk. This is cleaner in textbook examples than in messy real models. Treat it as the idea, not a precise law, but the point stands. Relationships become directions you can travel. So how does the computer actually use this to say two things are similar? It measures the angle between their arrows. Two words pointing in nearly the same direction, very similar, pointing at right angles or opposite ways, unrelated. That angle check has a name, cosine similarity, but forget the formula. The intuition is all you need. Same direction means same meaning. And that one measurement is the quiet engine behind almost everything. Find similar documents, recommend a similar song. Is this the answer to that question? It all comes down to one thing: how aligned are these two arrows? And here's what makes embeddings everywhere. It's not just single words. You can embed a whole sentence, a document, an image, a song, a product. Anything, as long as you can turn its meaning into a point in space. You can even put images and text in the same space, so a photo of a beach lands right next to the word seaside vacation. That's how you search images with text. And now every use case from the intro clicks into place. Semantic search. Embed your query, find the nearest document points. That's the lonely robot search from the start. Recommendations. Songs near the ones you love. And RAG, letting an AI answer from your documents, embeds your files, then grabs the chunks nearest your question. Embeddings are the foundation under all of it. So that's an embedding. You take meaning, a word, a sentence, an image, and turn it into a location in a vast space, where distance means similarity and directions carry relationships. Once meaning has coordinates, a computer can search it, compare it, and reason about it as math. That's the trick under semantic search, recommendations, and the whole retrieval side of AI. Fair warning, as always. I drew 3 dimensions. Reality uses hundreds. But the idea is exactly what you just saw. Now, once you've got millions of these points, how do you search them instantly? That's a special kind of database, vector databases, and it's my next video on screen now. Subscribe for AI explained visually, and tell me in the comments, what's a search that felt like the computer read your mind? That was embeddings.